Welcome to Differential Equations and Linear Algebra. My name is Adalbert Wiesgarter.
And my name is Jürgen Gross.
Alright, when connecting linear algebra and differential equations, the main equation that connects them is ax equals x prime. So A is the matrix that transforms vector x into x prime. And so this is where A is an m by n square matrix with linearly independent vectors.
X was represented as a position function where time is t. It will equal first a scalar, then the first eigenvector, along with e to the lambda 1 t, where lambda is the eigenvalue, plus, and depending on how many rows or columns you have, it goes on to c of n, v of n, which is the nth eigenvector, e to the lambda n t, where lambda n is the final eigenvalue.
We also have to have an x0 point. And in this case, we're going to make it 3, 2. If we have this equation here, then we will do an example problem. If we have the A matrix, which has n linearly independent columns, in this case, A will be a 2 by 2 matrix with columns as 1, 2, 6, 2. Then what we have to do is find the eigenvalues, which gives us 1 minus lambda, 6, 2, 2 minus lambda, which will give us, for the determinant expression, to find the eigenvalues, we have 1 minus lambda times 2 minus lambda minus 12 is equal to 0. So from here, we have 2 minus 3 lambda minus lambda squared minus 12 equals 0, which gives us lambda squared, that's a plus, lambda squared minus 3 lambda minus 10 equals 0, which gives us lambda minus 5 times lambda plus 2 equals 0. This means that our eigenvalues, also denoted as lambda, are equal to -2 and 5.
Okay, so as my partner found the eigenvalues right here, we will now be finding the eigenvectors by these eigenvalues. Okay, so I'll just erase his atrocious work and start my masterful equation solving. Okay, so we start with 3, and then there's 2, and then 4, and then we have our 6, as we had before, but now we have obviously the eigenvalues added, and then we must solve this. We'll reduce it and see how they are linearly dependent now. So obviously we will be getting an eigenvector, and so we can just turn these into this, and now we row reduce, and obviously you're solving for an augmented matrix, which is not clearly defined here, but it is all zeros on this side. And so we get an eigenvector defined by this 1. So when the eigenvalue is -2, we get an eigenvector of, so this is x1 minus or equals -2 x2, and then an x2 equals x2. So our eigenvector will be negative 2, 1. And so this is our eigenvector for this eigenvalue. So now I will have a student come in to do the finding of the other eigenvalue, well, the eigenvector for this eigenvalue. Now I will erase my beautiful, masterful work. This marker is absolute garbage. I am so sorry. Okay, now I have the student come in. Okay, so we begin with the matrix, obviously. He's trying his best to write this as well looking as he possibly can. Okay, now he is inputting the eigenvalues into the matrix. Obviously, you can see here that it is linearly dependent, the two columns of the matrix. Okay, now he goes. Yes. Okay, now you find eigenvector. I passed on the, sorry. I passed on the camera and I now discuss what he is solving. He's obviously solving for the eigenvector based on the eigenvalue of 5 at this point. It looks like he's done a very good job at this. Obviously, he has learned this from linear algebra. There is nothing different in finding eigenvectors here. I say that's a good job to you, sir. Thank you for passing the pen back.
Okay, so just to review, we have lambda 1 is equal to negative 2, lambda 2, lambda 2 equal to 5, and then we have eigenvector 1 is equal to negative 2, 1, and eigenvector 2 is equal to 3 over 2 and 1. So with these eigenvalues and with these eigenvectors and our x of 0 of 3, 2, we can create a matrix to find our constants C1 and V1. So we have negative 2, 1, 3, 3 halves, 1, and 3 over 2. And by row reduction, this will give us 2, 0, and 3 over 2, and 7/4, and a half. This means that we have C1 is equal to 0, C2 is equal to 2.
Okay, now after my colleague has finished his work, I will erase it all. Slowly and deliberately, as to not discourage him from his work again. I will remember those numbers, by the way. I am not stupid. Actually, what were the numbers? 0 and what? I believe it was 2. Okay, so as my memory is not horrible in any way, I will now be writing the answer. And it is obviously C1 will be 0. The V1 vector, because I have amazing memory and I remembered it, is negative 2, 1. And e to the lambda 1, which is obviously negative 2. And obviously the t is just the time. And then we add C2, which is, well, 2. And then the V2 vector, which is, okay, 3 half 1, and then e to the, obviously 5, as we recall. Yes. And yes, this is our answer. Right here.
Okay, now to finalize, we have x1 of t and x2 of t, which is equal to 0 times negative 2 times e to that expression is 0, plus 2 times 3 over 2 times e to the 5t is equal to 3 e to the 5t. And then we also have x2 of t is equal to 0 times 1 times e to the negative 2t, also 0, plus 2 times 1 times e to the 5t, which is equal to 2e to the 5t. All of this is equal to 3e to the 5t and 2e to the 5t. This is our final expression for x1 of t and x2 of t. Okay, now we have to discuss graphing. So, if I draw my graph here, this over here being x1, and this is x2. What we're going to do is graph our eigenvectors. So, we have our first one as negative 2, 1, negative 2, 1, and our second one as 3 over 2 and 1. So 3 over 2, 1, that's also equal to 3 and 2. So that brings us to about right there. And draw a line here through the origin, and a line here also through the origin. So these graphs of our eigenvectors will be our starting point. If we take another matrix, let's say A is equal to 1, 2, 3, 2. With this matrix, we are going to talk about graphing. We have eigenvalue 1 is equal to negative 1, and eigenvalue 2 is equal to 4. We also have eigenvector 1, which we will call u, is equal to negative 1, 1. And eigenvector 2 is equal to 2, 3. So, given all of these, we can now discuss graphing. If we draw our graph here, we will have x1 and x2. So, now we have eigenvector 1, negative 1, 1. So you will have negative 1, 1. That gives us a line like that goes straight through the origin. And we'll call it u1. And we also have eigenvector 2, which is 2, 3. There. Coming down like that. And that is u2. In this situation, we will have c1 is less than 0, c2 is greater than 0. This means that our u1, sorry, it's got a little messy. This means that our u1 will be going in here towards the origin, like this, and our u2 will be going away from the origin, like that. One other thing is that we do not need these c values. We can see that this eigenvalue here is negative, and that eigenvalue 2 is positive, which means the same thing as these, which means that your result will be the same as these graphs here. And so, since we have a saddle point here, we have, well, this is a saddle point here because we have going in and going out. See now, if both of these were negative, then everything would be going inwards. If both were positive, we would have everything going outwards along, the eigenvalue, or the eigenvalues. If both were positive, then everything would be going outwards. But in this case, since we have a small negative eigenvalue for u1, it will go inward just a little bit and then out. And then we keep drawing here in just a little bit and out in a little bit and out. And so this is also because this is such a large eigenvalue. So And so we will do this at all of these corners around the graph. In, out, in, in, out. This is what our field looks like when we are graphing a differential equation. So now another example. So I'm just going to erase. Okay, and so here, if we had both of these were less than 0, then these would be going in, here, in, towards the origin, which will give us a result of something that looked like this, going in towards the origin, going in, going in. So this is what it would be like if both were negative. It would be the opposite if both were positive. But this is the gist of graphing differential equations when you've solved it for all of its eigenvalues and eigenvectors. This is an introduction to differential equations using linear algebra. Yes, there are much further concepts beyond this, such as complex eigenvalues, which involve imaginary numbers, but that is a little bit too complex for this introductory lesson. I am Dr. Adalbert Wiesgerver, and this is my colleague,
Jürgen Gross.
Thank you for listening.